Hi, my name is Justin,
Hi, my name is Kent.
I'm Cindy.
and we're the Onshape Fluid Simulation subteam, where we model fluid flow and optimize designs with computational fluid dynamics. You can find more on our GitHub.
So throughout the semester, this is the entrance tank we have been trying to model the flow through. The entrance tank contains an inlet pipe and an outlet pipe, which is the L form. Here's an animation of depicting the flow of water through the tank. Here is a close-up of the inlet pipe showing the hose where the water flows out through the pipe. So we are trying to decrease the turbulence of the water in the tank because it's affecting the water flow rate. And the turbulence also affects the chemical dosage controller, which affects the dosing of chemicals in the water, such as chlorine and cleaning agents, which is dangerous because high levels can be carcinogenic, while lower levels can prevent water from being cleaned thoroughly. And so figure 3 shows the turbulence in the tank, and figure 4 shows the chemical dose controller. Here's a cutout of the entrance tank visualizing the inside, and here are where the inlet pipe and outlet pipes are located. And so we want to simulate the flow inside the entrance tank as accurately as possible. And one problem is that SimScale cannot extrapolate the flow between the two disjoint models. And we need to find a way to model the LFOM, which is the outlet, and the jet stream inlet, which is the inlet pipe, and find a way to model the inlet flow and the outlet flow. So we have decided to simplify the entrance tank and just treat it as a flow from the 3 inlet pipes into the covered tank through the 1 outlet pipe. This is the inlet pipe represents the jet stream flow, and the outlet pipe represents the outlet flow through the alpha. Here are 2 perspectives of the model. The red shaded circle represents the part where we define the boundary conditions of the model. And so some boundary conditions include the velocity condition and the pressure condition.
So as Kent mentioned, we first tested the velocity boundary condition where the inlet mean flow rate is 0.06 meters cubed per second and the outlet flow rate is 0.180 meters cubed per second. And these are the steady state solution plots after 1000 seconds in simulation time. And we noticed that there's a backflow in the second inlet pipe as shown in figure 9. And we also noticed that the 3 inlet flow rates are not the same as shown in the heat map on figure 10. We do see that there's very low turbulent kinetic energy on the top of the tank where we saw the problem of turbulence in the current tank design. So we plotted the residuals for velocity and turbulent kinetic energy, and we saw that the residuals are small in value and they reach a steady state around 200 and 400 seconds, but there seems to be instability at 900 seconds and then it decreases again to a new steady state. This is not the convergence plot that we want because we want a steady state solution that has little to no noise. And so we also did a simulation with pressure boundary conditions where the inlets have a total pressure of 300,000 pascals and the outlet is fixed at atmospheric pressure. We noticed that we solved the problem of the different inlet velocity behaviors over time where we also noticed that there's a lot of turbulent kinetic energy as shown in figure 13 because it is a small box with extremely large pressure. And so we also plotted the convergence plots and we noticed that the longer the simulation time, there's less residual and this convergence plot is a lot smoother and there's a lot less noise than the convergence plot with velocity boundary conditions. Therefore, we decided to continue using the pressure boundary conditions for the rest of the simulation models.
Yeah, so as Cindy mentioned, we decided to use the pressure boundary conditions. But now that we actually have a concrete idea of what boundary conditions to pick, we can finally accurately model the entrance tank and then run the simulations and get more accurate results to the actual entrance tank. So one thing to note is that we now need to find a way to mimic the behavior of the uh, inlet pipe jet streams where they hit a wall and make a 180 to the outlet pipe. So we did this by essentially elongating the inlet pipes all the close to the left wall, and we essentially have the outlet pipe, which is the LFOM, and usually it's submerged in the water, but we just approximated it as an outlet pipe on the top of the tank. So as 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 before, the red shaded areas uh, are where we define the boundary conditions, and Figure 16 depicts the inlet boundary condition. And the reason why we wanted to define that whole fluid volume as a particular boundary condition is because we want to mimic the jet stream behavior. We wanted a sudden we wanted the change from the inlet to the entrance tank to be sudden. So, and figure 17 depicts the outlet shaded area, which represents the boundary condition, which represents where we place the boundary conditions. And here's a bird's eye view of the entrance tank. And essentially, what differs from before is the fact that we have an open tank. Previously, the way that we were modeling the tank, it was a closed tank where there was a no slip condition at the top of the tank. However, because the entrance tank is open, we essentially want to model the top of the tank, the top fluid of the tank to be have a slip condition. This way, the fluid is allowed to freely flow at the top of the tank, almost mimicking an open tank. So, as Cindy mentioned, we wanted to use the pressure boundary conditions. So one thing to note is that we wanted to make the model as accurate as possible, and the pressures at each one of the jet streams of the inlet pipe are not going to be the same, and that's because of the changing elevation. So we decided to use the Agua Clara package and the Bernoulli equation in the form of head loss in order to calculate the pressure drop, the pressures at each point of the jet streams of the inlets. Now, depending on the type of elbow that we had, we would get a set of different results. We decided to stick with the larger set of pressures because we figured that if there was turbulence in at the very top of the tank and the larger pressures, uh, if there was turbulence at the very top of the entrance tank at the larger pressures, we would then change the elbow into the flange elbow with the lower pressures. However, if there was no turbulence, we could then safely conclude that with the flange elbow, there wouldn't be turbulence at the top of the tank. So, uh, yeah. So we note that the flange elbow pressure is on the order of 1.5 thousand pascals to 2.8 thousand pascals, and for the threaded elbows, it's around 4,000 pascals to around 5,000 pascals. So here's a pressure heat map visualizing the boundary conditions. We note that now it's more similar to a jet stream like behavior, where the pressure is constant throughout the inlet, and all of a sudden there's a change in pressure to almost the atmospheric pressure, which causes the fluid to burst out of the inlets, behaving like a jet stream. We note that the outlet here is we note that the outlet here is at around zero pressure, 0 pascals of pressure, and that's because we decided to set it as atmospheric. And we note that decrease the pressure is increasing as we go further down, as we go deeper into the tank, which is what we expected physically. So here are results with the threaded elbow case. We see that the fluid behaves like a jet stream as depicted in figure 21 with the projected velocity vectors onto the velocity heat map. And we note in figure 22, once again, we see that there is the lack of turbulent kinetic energy at the top. and there's mainly only turbulent kinetic energy where the jet streams first come out. And here are our convergence plots. As you can see, the convergence plots are all monotonic and also have residuals below the smaller than the order of 10 to the negative 3, which means that to some extent our model is physically modeling the entrance tank very well. And yeah, so the entrance tank. So we can see that our results are stable and uh essentially model the physical aspects of the entrance tank.
So from analyzing the simulations that we've done so far from the entrance tank, we were able to conclude that the turbulence is not coming from the jet streams entering the tank, because we saw that the jet streams dissipate in turbulent kinetic energy very fast. And the source of water flow stems from a waterfall, and we can easily see that the inlet contains water and air in this video, where we see that air bubbles are escaping, which may be the primary cause of turbulence at the top of the entrance tank. So for our future tasks, we hope to simulate our entrance tank design with air and water using the multi-phase flow option on SimScale to more accurately depict the actual flow of the tank and analyze whether air bubbles is the root cause. And in the future, we plan to create a manual for future simulations of modeling computational fluid dynamics for any part or pipes. And once we're able to simulate multi-phase flow, we'll be able to simulate other regions of the water treatment plant, such as problems with the baffles breaking when the water flows from the LFOM to the flocculator. Thank you.